Okay, welcome back. We'll continue with the one. So question is to transform an indeterminate frame with a degree of indeterminacy R into a determinate one, the number of plastic hinges are required. So we know number of hinges which is necessary to make the structure into an mechanism is N is equals to R plus 1. So R is number of statical indeterminacy. So R, the number of hinges is equals to R will make the indeterminate structure into determinate structure is C. Okay. Now next question. In a plastic hinge, the actual distribution of the strain so across the section will be. So read the question carefully. They are asking strain. Okay. The strain, if you are already familiar with the assumptions we make in RCC and all, so strain will always remain linear. So that is what, like the assumption, the plane section remain plane even after bending. This stands for here. Okay, this is only because of that, like strain is going to be linear even up to failure. Remember this. Okay, it's not just only up to the yielding, even up to the failure, the fracture. Okay, the strain will remain linear. Okay, so this is no, you cannot have this kind of, like, just think upon it, why this cannot be. You cannot have a strain like this. This is stress profile. Okay, so don't confuse the stress profile, but this is a strain profile. For all the cases it is going to be linear in all the kinds of the analysis problem. So which one of the following modes of failure is taken care of in plastic design of steel beam? The first one, a plastic material deformation throughout the beam. Plastic material deformation is, no, it's not throughout the beam, is only at some point. Okay, so the answer A is not the answer. Lateral buckling of, no, we don't talk about lateral buckling here. Elastic buckling of the compression, no, we don't take here. Hinge formation in the beam due to yielding of steel, so this is the correct answer. Now which one of the following is the load factor? So load factor we defined as an what is this, the MP by MA, that is working ultimate load. Okay, plastic moment divided by working load, plastic moment by working moment. Okay, so if you have this failure load by working load, live load by dead load, no, total load by dead load, no, dynamic load by, no, this answer is B. So neutral axis distance d1 at plastic moment condition for a triangular cross section is given by figure having similar properties in tension and compression is. So what they are asking is that, like, neutral axis is that the plastic moment. So what they are exactly meaning is that is the equal area axis. Okay, so where does it equal area axis goes? So we already did this one, and if you look into the lecture number 2, this is we have been talked about. Okay, we have taken this. So what is this h1? So okay, h1 is equals to, we get as h1 by root. Okay, h1 by root, here is our answer. Clear? So for this you can try this out once again and to check yourself. Clear? So answer for this one is d by root 2. Okay, answer is d by root 2. So we'll take up some more questions here. So some more questions. Okay, that's okay. So let's wait. The shape factor for a solid circular section diameter d is equal to. So what is the shape factor for it? We know 1.7, but it is not given, so we need to work it out. So what is this shape factor? Shape factor is going to be where it is. S is equals to ZP by ZE. Okay. Now ZE, I know ZE is equals to pi d cube divided by 32. So only I need to do is that, like, ZP. Okay, so ZP is equals to pi d to the power pi d square by 4 8, that's a by 2, and yc is equals to what? It is 2d by 3 pi. Okay, that's 2d by 3 pi yc and yp bar. And you can if you are not getting it, so if I draw a circle, this is where my neutral axis is. and this is the center distance yc bar. This is center distance yt bar. You're supposed to be master of all these things. Okay, practice. That's the key. Yc bar and yt bar. So I know we are now 4r by 3 pi. So and we know 2r is equals to d. So it's 2d by 4. So what I'm going to get here, pi d cube. Okay. So I is going to become 4d by 3 pi. So it's going to become 2. It's going to be 6 pi. Okay. So what this pi get cancelled, it is d cube by 6. So therefore s is going to become pi d cube by 32, okay, over d cube by 6. Okay, sorry, d cube, not d to the power of 6 is d cube. It cancel on what is this, 6 pi by 32. Do we have an answer? 6 pi by 32. No, don't have an answer. Oh, wait a minute. Z is same, ZP is also, yeah, it is pi d square by 4, it is a by 2 into this thing, d cube. That's fine, yeah. So we are not going to get pi will get cancelled, yeah. D cube. So why we are not getting here? There is no answer actually. Even I can make it 3. This is I can make it 16. So it is actually 3 pi, okay, by 16. So this should be the answer. There is no answers here. Look at this answer. This has been they made this ulta. Ah, correct. No, I'm wrong, Baba. Look at this. Look at the foolishness. What I'm doing here is supposed to be 1 by s. What I'm doing here. So answer is C. Okay, fine. A structure has 2 degrees of indeterminacy. The number of plastic hinges that would be formed to completely collapse. Yeah, we know n is equals to ds. Degree of indeterminacy plus 1 is the number of hinges are required. So 2 plus 1 is has to be absolutely 3. The answer is C. Okay, go on to the next question. The plastic modulus of a section is 5 into 10 raised to p. So this is plastic modulus ZP. Let's take it. Its shape factor is 1.2. Let's take it. Plastic moment capacity is equals to 120 km/meter. What is the value of yield stress of the material? So what I know, M is equals to Fy into Z. Okay. Now plastic modulus of the section itself is given, so not necessary for me. So Fy is equals to M by Z. Look at this plastic moment. This is MP itself. This is MP itself. Okay. So MP by is equals to Z. Right. So it is MP here. MP is 120. Okay. Kilonewton meter. And this is 5 into 5 into 10 raised to minus 4. So what I'm going to get here, so it's going to be 24. Okay, so this is going to be 24 into 10 raised to 4 kilonewton per meter square. Okay, so if I make this 24 to 40 meganewton per meter square, okay, so this is nothing but 240 MPa. So 240 MPa is nothing but Newton per mm square. Look at this answer we have seen. What is the ratio of shape factor for beams cross section having rectangular and circular and triangle shapes of same area? So this is actually based on, look at this, whatever may be the area, I know S for rectangle is equals to 1, S is equals to 1.5, right? I'm sorry. So this is 1.5, okay, for rectangle. It is 1.7 for circular. Yes, it is 2.34 for rectangle, right? So whatever may be the area, it is if it is same area, if all the areas are same, I need to take the ratio. So I am going to take the ratio in terms of rectangle. Okay, so what is this? Just divide by 1. So because they have taken the rectangle as 1, so it is going to be 1 is to 1.13. 1 is to 1.56. I did the calculation, so you are supposed to use to calculate. I don't know how to do this one. Okay, so the answer is C. Next, move on to the next question. The plastic analysis of a structure is applicable to the structure made of which of one of the following? Ductile and material. No, this is not applicable for brittle material. We know that one. We need large strain sustaining. Okay, any structure material, no. Brittle material, no. So it's only for ductile material. The value of shape factor is taken for rectangular section in plastic design. This is well known for us. This is 1.5. I'm sorry. In the plastic analysis of a steel beam, which of the following assumptions is are made? Play section under bending remain plane at all stages. This is absolutely true. We do it for all the bending cases. The stress strain relationship is bilinear because that is true. I'm sorry. So we take this linear, okay, straight line and straight line, bilinear, one linear by second linear. Okay, consists of two straight lines. So that's correct. Shear deformations are neglected. Of course, we neglect the shear deformations. So all the options are correct. Okay. So what is the distance between the elastic neutral axis and the plastic neutral axis for the cross section as shown in figure? Oh, that's beauty, yeah. So what I'm supposed to do? I am supposed to have my equal area axis. Okay. See, equal area axis. This is simple. What is the equal area axis? Which divides the section into two parts, right? Which divides the section into two parts. Now look at this. This flange 100 by 20 mm is equals to 100 by 20 mm. Okay. So this is my equal area axis. That's cool. You need to observe all these things in the examination. EAA. That's fine. Good. Here 100 by 20. That's fine. But only thing is that I'm going to have my neutral axis somewhere here. Okay, that I don't know. I need to calculate. So this is my neutral axis. Okay. What they are asking is this distance. What they are asking is distances. Now let's calculate where my neutral axis lies from the top fiber. How to calculate that? You calculate y bar. So this is what I'm going to take it as an y bar. Okay. So how to do it? Simple. 100 by take the moment. Organon's theorem and multiplied by 10 and then 100 multiplied by 20. Okay. Multiplied by what is this? 20 plus 50. This is going to be 70. Right. So divided by 100 by 20 multiplied by 2. Okay. So I can get out this 100. Fine. I can get 10 gone. Okay. So what is the left thing this here? 2 into 10, 20 plus 2 into 71, 40. Okay. Now this is 2 into 4. So how much this is? 160 by 4. What is this? 40 millimeter. So I'm going to get my neutral axis 40 millimeter. So from here to here it is 40 millimeter. Therefore this is going to be 20 millimeter. That is the answer. Answer is D. Okay. I hope today you are doing good. So once again go through all the problems, understand the question and try to solve by yourself. That's a skill. It will help you a lot. Okay. Chalo. See you in the next video.